This is the next video in the chapter on composition of solutions. We have just learned about all of the other ways that we can measure the concentration, including mass percent, volume percent, and parts per million. And now we're going to do several example problems to practice those skills. Let's start with this first example. Pause the video here if you need a moment to write this down. So our first problem says a solution of calcium chloride in water forms a mixture that is 36.5% calcium chloride by mass. If the total mixture is 145.4 grams, what mass of calcium chloride and what mass of water were used? So this is an example of a smaller scale problem where there's only a small amount of dimensional analysis to do. We can see that we have been given the mass percent of our starting material, and we've been given the total mass of the entire solution, both solute and solvent, and we are trying to find the mass of the solute calcium chloride and the mass of the solvent water. So we can use the definition of mass percent to help us here. If we remember from the previous video, the definition of mass percent was the mass of the solute over the mass of solution, which is the mass ratio, and then to make it a percent, it is multiplied by 100. So the part that we're looking for in this question is the mass of each of those parts. So the solute in this case is calcium chloride. So we can rearrange this equation to solve for that piece. So if we rearrange it to solve for mass of solute, we can multiply both sides by mass of solution, divide both sides by 100, and we will end up with the percent mass divided by 100 multiplied by mass of solution. That's the plan we're going to use to solve the question. So let's start with what we know. We know the mass percent is 36.5 for calcium chloride. And so mass percent is grams of that thing over 100. That's this part. 100 grams of the entire solution. And so then we're going to multiply that by the mass of the entire solution, which was 145.4 grams. And again, we can see that it's really important to start including not just the unit of grams, but also what we are measuring. The entire solution, just the calcium chloride, just the water. That compound is going to be important. So we can cancel grams of solution with grams of solution. And we can see our unit is going to end up being grams of calcium chloride. So if we type in 36.4 times 145.4 over 100 on our calculator, we should end up with 53.1 grams of calcium chloride in our 145.4 grams total. So that's one of the pieces that we wanted. And the other piece we want is the mass of water. So there are two ways to get to that because math is flexible. You can either subtract the 36.5% from 100 to get the mass percent of water, or we can just subtract the mass of calcium chloride from the total mass. So I'm going to choose to do that way. So we know that we have 145.4 grams of solution in total. That solution is going to be one part solute, which is calcium chloride, and the other part is going to be solvent, which is water. And if we do 145.4 minus 53.1, we should get 92.3 grams of water. So there are the two things that the question has requested. And as we just did, remember that the mass of the solute plus the mass of the solvent equals the total mass of the solution. So that's what we use to do this subtraction here. Excellent. All right, let's do one more example. This one was using mass percent to find individual masses. Let's do a problem where we have to convert between one unit of concentration measurement and another. So take a moment and write down this problem. This one says the sulfate ion level in a municipal water supply is listed as 46.1 parts per million. What is the molarity of the sulfate in the water? You can assume the solution density is the same as pure water, which is 1.00 grams per mil. So we can see our starting information. We're starting with parts per million, which is a mass measurement. We are trying to find molarity, which is measured in moles per liter. And we've also been given this number, which is the density of solution. When you're given a density, you want to be careful to check what the density belongs to, whether it's the density of the entire solution, the density of just the solvent, the density of just the solute. We need to be careful to watch what those units specify. And the density is going to be particularly important when we're doing conversions that move between mass and volume. Because remember that density is equal to mass divided by volume. So it's going to allow us to convert between those two systems. So there's going to be more than one step in our calculation here. So it might be useful to stop and get our bearings before moving on with the calculation. So our general plan here is we need to move from parts per million to molarity, and each of those has several different units inside of that one concentration measurement. So parts per million is a measurement of grams of solute over grams of solution, specifically 1 million grams of solution. And molarity, those units are moles of solute over liters of solution. So the compounds on the numerator and denominator are the same. Both of them have solute on the top and solution on the bottom, but the actual unit of grams and moles or grams and liters needs to change. So even though the left side, parts per million, only has one single unit, we can treat it as two parts, as top and bottom, and convert the top and bottom separately. That's one of the beauties of dimensional analysis. So for both of our solute terms here, to get from grams to moles of solute, we can use one of our favorite tools, molar mass, to help us do that conversion. And then for all things concerning the entire solution, we need to get from grams to liters. And we can use the density that we introduced over here that was included in the problem as a way of converting between mass and volume. So I'm going to combine both of these two types of conversions into one long dimensional analysis step. But we'll color code it so you can follow along with what we're doing. So we start with what we know. And what we know is that sulfate is present at 46.1 parts per million. So parts per million is a mass measurement of grams of the solute, which is sulfate. And we all remember our polyatomic ions as SO4 2-. 46.1 grams of sulfate per 1 million or 10 to the 6th grams of solution. We're expressing it now as the mass ratio by adding the 1 million to the denominator. Okay, so we have two conversions to do. Let's do the one on the top first. Oh, it looks like I spelled molar mass with an S. Mistakes happen. Okay, so we're trying to get from grams of sulfate to moles of sulfate using our molar mass. And we're going to take care not to use our molar mass upside down. So we want the grams to cancel. So we want the grams to be on the bottom. And I don't know what it is, so I'm going to leave a circle. Grams of sulfate, and we want to end up with moles. So we'll put 1 mole of sulfate on the top. And I like to do my setup before calculating the molar mass, so we'll just come back to that. Now we need to turn the bottom unit from grams of solution to liters of solution. And we can use the density given to do that, taking care not to use it upside down. So it's in grams per milliliters. We want to put grams on the numerator so that that cancels with our denominator, 1.00 grams of solution over 1 milliliter of solution. So now grams of solution cancels and grams of solution cancels. You see how especially important it is to include the compound because there is a grams value on the numerator and the denominator. So we need to be very careful about which one we're canceling. And finally, molarity is usually reported in moles per liter, and we've gotten stuck at milliliters, so we'll just toss on one extra term to convert from milliliters of solution to liters of solution. 1,000 milliliters, whoops, in 1 liter. So milliliters of solution cancels with milliliters of solution. That leaves us with liters of solution on the bottom and moles of sulfate on the top. So we're money, we're excellent shape now, except we've forgotten to calculate the molar mass. So we need to do that before we can calculate. All right, so we are going to have 1 sulfur, which is here in our table, and apparently completely unreadable. That's fine. You can take my word for it. Sulfur is 32.066. And we have 4 oxygens, which is here at 15.99. And we can add those up to get a total of 96.062. Now you may be wondering if anything changes when we're computing the molar mass of an ion, because this one has a charge and the number of electrons has changed, but we know that electrons are very, very light. They're 1,000 times lighter than protons or neutron, so changing the number of them doesn't significantly change the molar mass. So we don't have to take that into account when we are calculating it. So we'll toss that 96 into our computation, and then we can plug this into our calculator. 46.1 divided by 1 million divided by 96.062 times 1 times 1,000. And what we're going to get is the molarity. And another way that we can represent the molarity instead of writing the word all the way out is to write the compound the molarity belongs to and to put it in brackets. So SO4 2- in brackets means sulfate molarity. And if you plug that into your calculator, you should reach an answer of 4.8 times 10 to the negative 4th, and our units are going to be moles of sulfate per liters of solution. There we are. So some of these conversions between different units of concentration require several steps, and there needs to be a little bit of a planning process in advance to make sure you include all of the correct dimensional analysis terms in order to reach the final answer. But the units will be your guide. The units will tell you which steps are necessary in that conversion. Okay, we have now done so many examples with concentration units, and that means we are ready to check off the first learning objective under compounds, which is moles and molarity. We learned about moles way back in the beginning, but now we can do molarity. We can talk about how many moles of something are in a particular solution. And that is all for this chapter.